When we think about artificial intelligence, it's easy to picture a pristine, weightless brain living somewhere up in the cloud. It feels like pure software, elegant lines of code that you can copy, paste, and run. Building a frontier AI requires a massive industrial undertaking. While a regular application is relatively cheap to scale, training a modern language model requires massive capital. OpenAI's GPT-4 is estimated to have cost $78 million in computing power, and Google's Gemini Ultra reportedly hit closer to $191 million. Those price tags are already looking quaint. Industry projections show that the next major generation of training runs is on track to cross the $1 billion threshold. This equation shows the math underlying deep learning that drives these costs. During training, a neural network learns by performing vast numbers of calculations, called floating point operations, or FLOPs. A widely used approximation for this is simply 6, multiplied by the number of parameters in the model, multiplied by the number of training tokens, or words it reads. When you build models with hundreds of billions of parameters and feed them trillions of words of data, that equation explodes. The compute budget for today's leading models easily surpasses 10 to the 26th operations. That's a 1 with 26 zeros behind it. You cannot write a clever piece of code to get around a math problem that large. Performing that exact number of calculations demands raw brute force, which requires the construction of massive physical supercomputing infrastructure. The core engine of that brute force is the AI accelerator chip. Unlike a standard computer processor that handles tasks in sequence, these accelerators are designed specifically for massive matrix multiplications, crunching thousands of math problems simultaneously. Because of that highly specialized design, a single unit costs tens of thousands of dollars. By the time you configure a full server, you are looking at a machine that can easily run north of $300,000. One server is just a fraction of the requirement. Training a leading model means buying and linking 10,000 or more of these accelerators and running them continuously for months on end. You cannot plug 10,000 graphics cards into a wall and expect them to work together. They have to function as a single unified brain, which requires an incredibly dense web of proprietary, high-bandwidth interconnects. This diagram shows how the process, called gradient synchronization, works. Every time a chip learns something from its piece of data, it has to constantly and instantly communicate that update to all the other chips across the network. Building the infrastructure to support that communication is a massive expense on its own. The specialized networking cables, switches, and high-speed storage systems can account for anywhere from a quarter to over 40% of the total hardware budget. If there is even a microsecond of delay or a communication bottleneck in those cables, thousands of chips sit idle waiting for data. When you are paying thousands of dollars an hour to run the system, those fiber optic cables are just as critical to the operation as the processors themselves. Zooming out to the facility scale reveals the immense physical toll of keeping that system online. A training cluster of this magnitude draws tens of megawatts of continuous power, requiring specialized industrial electrical substations just to deliver the necessary current. That extreme power density generates an immense amount of heat. Without specialized industrial-scale cooling facilities pumping liquid or massive volumes of air through the server racks, the silicon inside would literally melt under the strain of the workload. This volatile physical rig requires teams of specialized infrastructure engineers, research scientists, and data curators to keep it from failing. Their primary goal is maximizing a metric called model flops utilization. It is a measure of how much of that expensive theoretical computing power is actually being used. Even in a well-optimized run, machines only hit a fraction of their peak capability, and it takes elite human talent to squeeze out every drop of efficiency to prevent millions of dollars in idle compute time. Because that specific expertise is so scarce, personnel costs are staggering. When you factor in compensation and research development, the human capital required can account for nearly half of a model's total development cost. A finished AI is rarely the result of a single, clean training run. The entire process involves massive pre-training phases, followed by continuous refinement, fine-tuning on highly curated data, and extensive human-in-the-loop alignment. Each phase burns through additional compute time. When you hear about a $100 million price tag for an AI model, you are looking at an amortized receipt for all of that physical orchestration, the silicon chips, the power grid, the cooling systems, and the engineering talent. There is a paradox in this industry. Every year, hardware gets roughly 30% more cost-effective, yet the relentless drive to push the absolute limits of intelligence outpaces those engineering gains. As labs race for higher performance, the total cost of training frontier models is growing by 2 to 3.5 times annually. The sheer capital required to build and power these physical clusters has created an almost insurmountable barrier to entry, locking smaller companies out of the absolute bleeding edge of the market. The trajectory of artificial intelligence is a brutal geopolitical race to secure specialized silicon, energy grids, and the most complex physical hardware on Earth.